Hey, I just wanted to quickly plug that if you guys want any tutoring, some new slots have opened. If you look in the description, there's a link to my physics and maths tutor profile in which I do tutoring on there. Hello everybody, welcome back to another episode of the A-Level Cookbook. Today we're going to be doing OCR A-Level Chemistry A, paper 1 from June 2017, so let's go. Now it says which one of these is not an isotope of iodine. So an isotope, remember, is where you have a different number of neutrons, and that's about it, right? So if I look at my periodic table, then the proton number of iodine is 53. So it's got 53 protons. We need to have a look at this and see which one of these do not add up to their respective proton numbers. So 72 plus 53 does give you 125. So that is indeed an isotope. Then if I do 74 plus 53, then we get 127. That is one of them. Then if I do 75 plus 53, I get 128, which is correct here. And if I do 77 plus 53, I get 130. But hold on a sec, that's not 130. So it must mean the proton's gone up, so it's not an isotope of iodine, so it's D. There you go. If you change the number of protons in an element, you've changed what element it is. So for example, iodine has a proton number of 53, but xenon has 54. So by that, it's got to be that. Done. What is the bonding between the ligands and the metal ion here? It's dative covalent, so it's D. There you go. Next, it says, what's the oxidation number of Mn and K2MnO4? So here, this is +1, but there's two lots of +1. So this whole ion is going to be MnO4 2-. Oxygen has an oxidation state of -2, but there's 4 lots of that, so it's -8. So -8 plus some mysterious thing here equals -2. So that means it's got to be +6, which is C. There you go. Now it says which calcium compound has the greatest percentage by mass of calcium. So we have CaCO3, NO3 2, and then we have CaOH2, and then CaSO4. So if we're looking percentage by mass of calcium, it's going to be the MR of the calcium divided by the MR of like everything else times 100. So it's going to be whichever one of these is the lowest, because if we have the lowest of this, we'll have the greatest percentage by mass of calcium. So if you look at the CO3 ion, that's going to be 12 plus 3 lots of 16, right, which is 60. So that carbonate ion is 60. Nitrate is going to be 14 plus 16 3 times, right? But then there's 2 of them. So if we times that by 2, it's 124. And then hydroxide is going to be 16 plus 1, but we're timesing that by 2, so that's going to be 34. And then sulfate is going to be 32.1 plus 4 lots of 16, which is going to be, what, 96.1. So therefore, remember that this bottom number being bigger means you're going to have a lower percentage by mass of calcium. So we want the one that has the lowest of everything else that isn't calcium. So in that case, it's got to be C, because that's only 34. If we have whatever the MR of calcium is versus, AR, sorry, divided by 35 times 100, that'll give you the biggest number. These are all huge, so we'd outweigh them, so that's out, so it's just C. Now it says 0.02 moles of calcium oxide is reacted completely with this much HCl. What volume in centimeters cubed of this much HCl is required for this reaction? So just real quick, sketch out what's happening. CaO plus HCl, you need to have CO2 plus HCl minus, you're going to have 2 HCl's. So that means if we have 0.02 moles of calcium oxide, the moles that you would need of this is going to be 0.04. Now they've told you that the concentration is 2 moles per decimeter cubed for this, but we need the volume. So N equals CV, V equals N over C. We've just worked out the moles that we want for this, which would be 0.04 divided by its concentration, which is going to be 2, right? So if we do that, we end up getting 0.02. However, that's in decimeters cubed, because moles per decimeter cubed is how we measure this, right? So then to convert that to centimeters cubed, you times it by 1,000, which gives you an answer of 20, so it's B. Now it says how many electrons are removed from this many grams of Ne to form Ne gas. So again, quickly sketch out what's happening. Ne gas becomes Ne plus gas plus E minus, right? So it says how many electrons. So we need to work out, first of all, the moles of this gas, because remember the moles can then help us find out how many of things we've reacted. If we look at this, the moles of the gas is going to be 2.02 times 10 to the minus 2 divided by its AR of Ne, so that's going to be what, 20.2. So the moles of this is going to equal 0.01 moles. So that means we're going to have 0.01 moles of electrons. Mole is just a unit. It's if I have 1 mole of bananas, I've got 6.02 times 10 to the 23 bananas. So this means that we have, in this equation, we have 0.01 times 6.02 times 10 to the 23 Avogadro's number electrons. So if that's the case, it's going to be C. A lot of people don't realize that. The masses in your periodic table, have you ever wondered why carbon is 12? It's in grams per mole, meaning 1 mole of this weighs this many grams. So if you have 6.02 times 10 to the 23 carbon atoms, it will weigh 12 grams. If you have 6.02 times 10 to the 23 Ne, then you'll have 20.2 grams of it. That's why it's those numbers. So if 1 mole gives you this many grams, 1 atom would be this divided by the number in a mole, which is 6.02 times 10 to the 23. There you go. So silicon can be made by heating silicon tetrachloride with zinc. 8.5 grams is reacted with an excess of zinc. The percentage yield is this. What's the mass of silicon made? So we need to work out the moles of SiCl4. So the moles of SiCl4 is going to be 8.5 grams divided by its MR, which is 28.1 plus 4 lots of 35.5. If I do that, we get, it gives you 0.04997, right? Now, these are in a 1-to-1 ratio. In theory, you should have this many of the same, right? But they've told you the percentage yield is that. So the actual moles of the silicon that is made is 0.90, the percentage, times this, 0.04997, which is going to be 0.04497 moles that we actually make. So then the mass of the silicon is just going to be moles times the AR, which is going to be your answer that we just got, times the 28.1. Times 28.1 gives me a nice answer of 1.264, which is A. When you want to work out the percentage of something, all you do is you times it by a decimal, right? So here's a little quick shortcut. For example, if I want 98% of, 6, you would do 6 times 98 over 100. Or you could just do 6 times 0.98, right? But if, for example, if we take this, so 98% of 6, to actually work from that, you would go for, so like 98% of 6 would be then 6 times 0.98. But to go backwards, right, if you're going this way, you times it by 0.98. To go the other way, you'd undo this by dividing by 0.98. So to undo a percentage, to get back to 100%, you can just divide by the percentage. So for example, if I was told that, like, I don't know, 936 is 28% of x, then I know that initially they must have done x times 0.28 to give you 936. So the original, which is 100%, remember, would just be this 936 divided by the percentage that it is. There you go. And it works for things like 100%. So if I have, like, I don't know, 275 is 110% of something, I know the x original has to be 275 divided by its percentage as a decimal to undo them, which is 1.1. There you go. All right, 4 pairs of solutions are mixed. Which pair of solutions makes a white precipitate? So let's have a look, shall we? When you're doing multiple choice questions like these, right, it's usually a lot of the time either multiple choice where one is right and the other ones are wrong, or it's single best answer, meaning that all of them are technically feasible. Here, you need to look for the killer straight away in each of these and be able to recognize immediately what's happening. If I'm making a white precipitate, to me, white precipitates are like carbonates and sulfates, like barium sulfate and metal carbonates. So immediately I can see I've got BaCl2 and something with a sulfate, which means I'm going to make barium sulfate, so immediately that's the killer. It's gone, done, finished. This, if you added the NH3s, you'd get like a brown precipitate. This, you'd get a cream precipitate. And then this, NH4Cl and NaOH, you'd get no precipitate. Enthalpy values are provided below, and they've told you the enthalpy of reaction is this, the bond enthalpies are these, and this is what's the bond enthalpy of this HI bond. So a lot of people like to do bonds made, bonds broken. I'm going to do a Hess's law cycle, because Hess's law cycle just makes sense in any enthalpy change in the universe. So you write your overall equation, and remember that every single arrow is an enthalpy change. So this one is the delta HR, which they've told you is minus 9 kilojoules, right? And that makes 2 HI. Now, the enthalpy change, the bond enthalpy change is the mean enthalpy change required to break 1 mole of bonds, blah, 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 right? So basically, essentially what you're doing is you've got 1 mole bond, and it ends up becoming atoms, right? So this is a bond enthalpy they've given you. So we're going from 1 mole bond to atoms. This is a bond enthalpy they've given you, so it's going from 1 mole bond to atoms. So a good start is that we're probably going to have atoms at the bottom of this, because here we've got not 1 mole per se, because there'll be 2 here, right? We've got bonded stuff, bonded stuff, bonded stuff, so they're all going to be bond enthalpied. So then these arrows go downwards like that. If that's the case, then the HH bond enthalpy to go from a 1 mole bond to its atoms is going to be 436, and then from here it's going to be plus 151, and then from here it's going to be, well, it's going to be plus 2 lots of X. We don't know what it is because that's what the question wants us to find. The enthalpy changes for 1 mole of bonds, but here we've got 2 HIs, remember? So it's 2 of them, so it's 2X. So then what you're going to do is you're going to say, well, if you start here and finish here, the enthalpy change in the middle should be the same as whatever root you have, because as long as you start and finish at the same point, it does not matter. So that means you're going to have minus 9, this enthalpy change equals all these other ones. So following this arrow, so it's going to be plus 436 plus 151 minus 2x. If I tidy this up, I get minus 596 equals minus 2x, then x equals this divided by minus 2, which gives you 298, so plus 298, which is going to be C. There you go. Now it says a reaction is 0 order with respect to reactant A. Which of the concentration time graphs for reaction A is correct? So remember, they're putting concentration here and time here. So if this is 0 order with respect to A, what that means is that the rate equals K times whatever A to the power of 0. As in, no matter what you do, 2, 3, 4, 5, whatever, this stays as 1, the rate is unchanged. We're looking at concentration and time, okay? So if the concentration is going down with time, because it will react, and it stays the same, then that's what it's going to be. Because if it was, for example, if it was first order, then as this concentration goes up, this would go up, but as this concentration goes down, this would go down, right? It'd be less steep. So Here, concentration against time, the change in concentration over the change in time is your rate, which you can see is the change in your y over the change in your x, which is the gradient. So if the gradient is the rate, right, another word you can think of is steepness. So if the steepness is changing, the rate is changing. If the steepness is constant, the rate is constant. Here, the gradient is a straight line, which means its steepness is constant, which means its rate is constant, which means no matter what the concentration of A is, even if it's going down, it's still constant, which means it's zero order, which is A. So that's one way of making sense of it, really. Aqueous Cr3 plus ions are reacted with an excess of aqueous sodium hydroxide. What product is formed? So if we've got Cr3 plus, right, Cr3 plus, that's going to be, in reality, CrH2O6 3 plus, and we're adding an excess of OH minus. If we're adding lots and lots of OH minuses, what we're going to end up getting is we're eventually going to get to that point where it's CrOH3H2O3, which everyone loves, right? But this actually goes further, and eventually what happens is all those other H2Os are booted off, and you end up with this, CrOH6 minus 3 plus, which is going to be A. The question told you it's excess, so eventually all of those are gone, done, finished. HA and HB are two strong monobasic acids. We mix this much with this. What's the H plus concentration of the resulting solution? So what I do is I just quite literally say HA, HB. We're going to have like HA and HB, and I just work out what their things are, right? So in this case, if it's monobasic, when we're mixing this much of this, we're going to work out the moles of HA. Well, sorry, moles really before and the moles after. So the moles of HA and HB, so initially we have no mixture of HA and HB. The moles of HA is going to be 25 divided by 1,000 times 6, which is going to be 0.15. And the moles of HB is going to be 45 divided by 1,000 times 3, which is going to be 0.135. If you have a strong monobasic acid, for example HCl, it dissociates into H plus and Cl minus, but because it's strong, it's so far to the right. The concentration of H plus is essentially the same as this, right? However, we can't really just go ahead and jump to doing that because we've got differing amounts of these. So the moles after of these two, in theory, are going to just mix together. So you're going to get those two added together. So 0.15 plus 0.135 is how much of the mixture of this you have left, 0.285. Obviously, we've got 0 of this and 0 of this on their own. They're not technically reacting. It's just a mixture of, is what I'm working out. So in this mixture of this, we have this many moles of each monobasic acid. Therefore, the moles of H plus is going to be 0.285. So then the concentration of H plus is just going to be this mole, 0.285, divided by the new volume, which is 25 plus 45 over 1,000. If we do that, we get 4.071, which the closest answer to this is going to be C. There you go. So mixture of N2 and O2 have a total pressure of this. The mole fraction is this. So mole fraction, remember, is your moles over your total moles. Your total moles have to add up to 1, as in your total's got to be, like all your mole fractions adding up has to be 1. Therefore, the mole fractions of O2 has got to be 1 minus 0.7, because the only two gases here are that. So if that's the case, we have 0.3. The partial pressure is going to be your total pressure times the mole fraction, which is going to be 1.42 times 0.3. If you do that, you end up getting 426, which is B. Done. Then it says a cell is constructed with these two redox systems below. Which of the statements is correct for this cell? So if we have a look, this one's more negative, so that's oxidized. This one's being reduced. Cool. So then it says the options are the cell potential is this. So E cell, remember, is E reduced minus E ox. So if we do that, we get 0.8 minus 0.34. That one is incorrect because it gives you 0.46 plus of that. So that one's out. It says the reaction of the copper electrode is this. So if we have a look, the copper electrode is being oxidized. So it's going from a solid with an oxidation state 0 to +2. So that's being oxidized. So that one is true. The silver electrode increases in mass. So if you have a look, this one's being reduced. This is reduced. So it's going this way, so we're going to get more of this, and that one's true. So it's only 2 and 3, which is going to be C. There you go. Now it says which electrode configurations are, is, or correct. So if we have a quick look at the periodic table, if I just grab it one sec. So one quick way of reading the periodic table is everyone knows that the S, this is the S block, this is the D block, and that's the P block, but a lot of people don't actually realize how that helps. This is period 1, period 2, period 3, period 4, period 5, period 6, period 7, and so forth, right? And across this is your groups. So if I pick, for example, I don't know, let me think. Let me zoom in because I can't read. Let's say we go with bromine, right? I know that bromine is in period 4. The period tells you the outermost electron shell number, so 4, right? And I know it's in the P block, so it's going to be 4P, and then it's 1, 2, 3, 4, 5. So I know that bromine's going to have an electron structure that eventually ends in 4p5. The same applies for the transition metals. The only difference, remember, is that these are in period 4 because they have 4s, blah, 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 3d something, right? So in that case, this is 3d1, 3d2, 3d3, 3d5, 3d6, 3d7, 3d8, 3d10. You might have wondered why I skipped these two out. These two are the weirdos that don't like to be the same. because that technically CR would be 4s2 3d4. However, it prefers to have 4s1 3d5 instead. So this is actually 3d5, and for the same reasons here, CU would rather be, instead of 4s2 3d9, it would rather be 4s1 3d10. Those are the two odd ones out. So remember, it's d1, d2, d3, d5, d5, d6, d7, d8, d10, d10, like that. All right, so if we come back to this then, it's easier to just do a quick shortcut around all of this. So we know that chromium likes to be 4s1 3d5, right? So 4s1 3d5, which you can see is the case here, so that's correct. Cu would rather be 4s1 3d10, just like I said, so that's correct. And then Fe2 plus, if we look, Fe is d1, d2, d3, d4, d5, d6, so it'd be 4s2 3d6, but it's lost 2 electrons, it's 2 plus, but remember the 4s empties first, it's going to be 4s0 3d6. So if that's the case, it's got to be this, which is not 4s0 3d6, so that one's incorrect, so it's only 1 and 2, so it's got to be B. This question is about ions and compounds using hydrogen. So the lithium aluminium hydride contains the AlH4 minus. Ion draw a dotted cross diagram to show this and show the atomized electrons. So aluminium likes to chill in group 3, right? So 1, 2, 3, yeah? But then it's got 4 H's on it. So 1, 2, 3, right? But we still have 1 extra H. And these are all covalent, so there's extras here. But then we still need 1 more. So here, there must be an H, but we don't have enough electrons for you. We only have H electrons left, so it's this. There must be an extra electron here, and that's what gives you this. Like that, it's minus. Now it says, nitrogen forms NH4 plus and NH2 minus ions. Predict the shape and name of these, the bond angles in these, basically. So NH4 plus, right, it's N, H, 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 H. So it's 4 bonding pairs and 0 lone pairs. So it's going to be tetrahedral, and it's 109.5. For NH2 minus, N likes to chill in group 5. So 1, 2, 3, 4, 5, right? If it's H2, then 2 of them are gone here for the H's, like that, right? That would be NH2, but it's NH2 minus, implying there's an extra electron in here. So we've got 2 bonding pairs and 2 lone pairs. 2 bonding pairs, 2 lone pairs means that you've got non-linear or bent, and the angle is 104.5. Whoops, 104.5. There you go, degrees. So nitrogen, phosphorus, and arsenic are in group 5 or 15 in the periodic table. The boiling points of them are shown below. So for NH3, it's got the highest boiling point. Then it's P and AS, which AS is the next lowest, and then P is the lowest. So it says, explain why the boiling point of pH3 is lower than the one of NH3. So when you're boiling something, what you're doing is you're overcoming some sort of force by breaking it. We're not breaking covalent bonds, right? Because if I have Cl2, for example, and I have it as a liquid and I'm boiling it, I'm not breaking these across, otherwise I'd have Cl atoms, which is incorrect. We're breaking forces between the molecules that are holding them together. Those forces between molecules are called intermolecular forces. They're only between molecules. You wouldn't find it in an ionic compound because it's not a molecule. So if you have like Fe, Cl3, that's not going to have intermolecular forces because it's not a molecule. Inter, between, molecular, molecules, right? So we're looking at pH3 versus the N. The only difference between them is that NH3 has hydrogen bonding because so H bonded to NORF gives you that. So NH3 has hydrogen bonding, which is stronger than London forces in the pH3, therefore more energy needed to overcome, and there you go. Explain why the boiling point of pH3 is lower than that of ASH3. If you look at pH3 versus ASH3, both of them have London forces, and they have got dipole-dipole interactions too, but they're both that. The only fundamental difference between these two is that this is bigger and it's got more electrons. So that's the only reason it could be different, and that's exactly why, actually, is that the AS has more electrons than the P. So therefore, ASH3 has a higher boiling point because the London forces are stronger. When you're doing these styles of questions, you need to do comparative statements, but also if you're stuck, just look at them and compare them with each other. I'm not sitting here trying to memorize what ASH3 is. It doesn't come up that often. All I see that's different is that this is now different, and for some reason, these are the results we see. That's literally it. So then I use my head to think, oh, what's an explanation for that? That would make sense and works, and it's exactly that. There you go. This question is about group 2 and group 17. Barium chloride can be prepared from barium hydroxide in neutralization reaction. Write an equation for this, and then state symbols are not required. So just write what you already know. You know that you're going to be reacting barium hydroxide, so that's BaOH2, and we're reacting it with... Oh, it doesn't tell us what we're reacting it with. No big deal, because it says we can make barium chloride at least. So we're adding it with something to it to make barium chloride, Cl2. So you need to think, what can I use to put chlorides into this? HCl, right, which is an acid, and that's neutralization 2. So if there's OH2, there's 2 plus, 1 minus, we're going to need 2 HCl's, so we're going to make 2 H2Os on this side as well to balance it out. Done. The reactivity of group 2 elements in MgBa increases down the group. Explain why. So a lot of people love to just say atomic radius, ionic radius, blah, 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 and then have absolutely no clue what to say beyond that. When you're going from here to here, the outermost electron is further away. So rather than jumping ahead and saying atomic radius, ionic radius, because what if it was Mg2 plus and Ba2 plus? Instead it said the reactivity of ions. If you said atomic radius, you've lost the marks immediately. So just talking normal people words, you know? As you go down the group, there are more shells. Therefore, there's increased shielding of the outermost electrons. Then I guess you could go ahead and say, yes, I've increased atomic radius. But you can only say that if they are atoms, and we're dealing with atoms here, that's fine. But sometimes people say it when there's ions and they get it wrong, right? But then that still doesn't explain why the reactivity is going higher. The reactivity is higher because those outermost electrons, when they are reacting, they're losing electrons. So for some reason, this means they lose electrons more easily. So what happens is the electrons are more easily lost, less energy is needed to remove them, because something about the shielding is doing that, because there is less attraction between these electrons. You need to think what they're going to be attracted to, the electrons and the nuclei of the elements. There you go. You have to explain step by step what's going on. You can't just say like bits and bobs and that's it, done. On gently heating, this compound undergoes this reaction. This reaction is an example of disproportionation. What is disproportionation? And show that it's taken place. So you can't really say species here, because loads of people love saying that. It's oxidation and reduction, or simultaneous. I was going to say simultaneously, but simultaneous oxidation and reduction of the same element. You can't just say species, because that's not narrowing it down to an element. It could be like a piece, if that makes sense of things. Like, for example, a compound could be oxidized or reduced as well in that sense, if you look at it in the whole sense. So if I look at this, we've got KClO3 minus. We have ClO3 minus, right? Minus 2, but there's 3 lots of them, so it's going to be minus 6. To make a minus 1, it's going to be plus 5. So that means Cl was plus 5, and it's become 2 in KCl. It's been minus 1. So here, you need to say whether it's been oxidized or reduced, right? So in this case, if it's gone from plus 5 to minus 1, it has been reduced. And then here, KClO4, this ClO4 has got to be minus. That's minus 8. And here, that's going to be something that makes plus minus 8 to be minus 1, so it's plus 7. So in the KClO4, it's gone to plus 7. So that means if it's gotten higher, the oxidation number, it's been oxidized. There you go. What is the systematic name for KClO4? So it's potassium chlorate, but then you have to include the oxidation state of the chlorate. You can't just do it without. So then here, the oxidation state of this is 7, so it's VII. There you go. So 2 changes are described below. For each change, write an equation including state symbols and explain how the entropy changes. So it's the reaction of barium nitrate with aqueous sodium sulfate. So in this case, we're going to write down what you know you're reacting. So BaNO3 to aqueous, because they've told you it's that, plus aqueous sodium sulfate. So Na2SO4 aqueous gives you, and you need to think what we're going to make. Barium, chloride nitrate and stuff like that, plus a sulfate should scream to you that you're making barium sulfate. Is the test for adding sulfate. So we're going to be making BaSO4 solid, and then these NO3s are going to go to this Na2SO4, so we're going to make 2 NaNO3 like this, aqueous. There you go. Then it's quite easy doing equations like this, because you don't have to think about, doing some deep thinking. You just work with what we have. So here, then, we're looking at entropy change, right, which is a measure of disorder. So we're looking at how disordered things are by basically how many ways you can distribute the energy and rearrange them and this and that, blah, 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 right? So if we have an aqueous thing here and an aqueous thing here, you'd be tempting to be like, oh, we've got 2 moles here and then 3 here, but aqueous, solid. The state matters as well. If this is solid, those particles are just sitting there vibrating in situ. In this case, the actual entropy change is negative. It's actually decreased, because BaSO4 is a solid. Therefore, there's less disorder. Cheeky. The equation that accompanies the standard enthalpy of change of atomization of iodine. So you need to know what that is. It's the enthalpy change when 1 mole of gaseous ions is produced from an element in its standard state. So we've got 1 I gaseous here from its element in its standard state. It exists as I2 solid, and it's going to be a half. You can't do 2 here. You're not allowed that, because the definition says you're making 1 mole of gaseous, so it has to be a half here like that. So here then, what's going on is our entropy change. Well, we're going from a half I2 to one of these. The entropy, and it was solid to gas as well. So then delta S is positive. The entropy increases. Why? Because we're going from solid to gas. Therefore, there is more disorder. There you go. This question's about Gibbs free energy change, enthalpy changes, and delta H and delta T, whatever, right? And it says, here's the equation. A chemist investigates a reaction to find how delta G varies with T, and the results are shown here. And it says, what's the significant about the gradient of the line and the values P and Q shown in this figure, and explain your reasoning. So this question should not really be that tricky. A lot of people panic over it because they're like, oh my god, I've got to memorize it. Dude, it's a straight line. Every single straight line in the universe is y equals mx plus c, where y is just your y-axis, m is just your x-axis, this m is your gradient, and c is whenever x is 0, which is here, this axis here. When all of these values is when x is 0, because x is this way, right? So that means that's going to be your y-intercept. All you need to do is compare it to the graph you have and see what's changed. So then if we look here, our y-axis is delta G, our x-axis is temperature, Well, I'm not thinking too hard about the y-intercept just yet, but I can if I want to, but I'm not really thinking about it too hard. Now, I know these two. Let's compare it to the Gibbs free energy change equation. So delta G equals delta H minus T delta S, right? So if we look, Ry is delta G in this example now. Rx is T. M is what's timesed onto it, plus C. If you look here and here, the M that's timesed onto it has got to be minus delta S. Because you can see that's positive. Y is on this, that's positive. So that means our M, our gradient, has to be minus delta S. And if you can see here, y x plus C, mx plus C, right? This bit's all dealt with. The only thing left is delta H. So that our C has to be delta H. The same thing applies for ln k equals ln A minus EA over RT, right? If they put y as ln k and they put the x-axis as 1 over t, then if you compare this to y equals mx plus c, ry is now ln k equals m times 1 over t, right? 1 over t plus c. Compare them now. So if you look at our 1 over t here versus our 1 over t here, this m must be this minus EA over r. So the gradient of this curve would be minus EA over r. And then whatever's left over behind all of this has got to be r plus c, so plus ln a. So c has got to be ln a. So that's how you do these. So in this example here, they're talking about that. So now Gibbs free energy change, right? The gradient is here. So in this question, they expect you to link it here as well. So in that case, basically everything I've written there on that side would come here. So write that, basically. And then eventually you would say that the gradient equals delta S, but negative delta S. It has to be negative. It has to be negative because y equals mx plus c, but delta G is minus t delta S, right? The x-axis is just t, not negative t. So that means you have to times on negative delta S. So the gradient's that, there's that. Then if we look at where P is where it's touching the y-axis, where x is 0, which is our y-intercept. So P must be delta H. And then Q, let's look at what Q is. So if we look where Q is, it doesn't really show us a nice little thing in the formula, but if we look carefully, this is some value of T where delta G or our y-axis is 0 because it's 0 across every single value here, right? So that means it's when delta G is 0 and it's the temperature when delta G is 0, which is when the reaction is feasible, and below this it's still feasible. And above this, you can see that when you get above this, delta G is now positive, which means the reaction is no longer feasible. That's it. Iron can be extracted from its ore, Fe3O4, using carbon. Several equilibria involved, and here's one of them. And says, why is equilibrium a heterogeneous equilibrium? All it means is that the species or the things are in different phases. So species in different phases, because you can see that we have solid here, solid here, but gas there. So it's heterogeneous by that. Then it says, write an expression for Kp for this. So Kp is a gas equilibrium, which is going to be a product of your reactants. The only thing that's gaseous here is that. So it's going to be PCO to the 4. That's it. Can't put these in because they're solids. Be careful. Now it says the forward reaction is only feasible at high temperature. Show that the forward reaction is not feasible at this and calculate the minimum temperature in K for the forward reaction to be feasible. So we've got to do a multiple bunch of steps here. First of all, we need to figure out, well, delta G equals delta H minus T delta S. Write down what you know. So delta H is, in this equation, here, plus 676, right? So plus 676.4 kilojoules per mole. Delta S for this equation is in 701 plus 703.1 joules per Kelvin per mole. We need to convert that to kilojoules, or the other way around. You can convert this to joules. I'm going to keep it in kilojoules because it's just easier to work with. So if we turn this joules into kilojoules, we need to divide it by 1,000. So it's going to be plus 0.7031 kilojoules per Kelvin per mole. Then our temperature, they've told us, is 25 degrees, but we need it in Kelvin. So it's going to be 25 plus 273, which is 298 Kelvin. So then delta G is just going to be these numbers slapped in. So 676.4 minus the temperature, 298, times the entropy change, which is 0.7031. If we do that, we end up getting 466.87 kilojoules per mole, which is roughly, 467 kilojoules per mole. And then you would say, well, delta G is, greater than 0, therefore it's not feasible. So that's the first one done. Then it says calculate the minimum temperature at which this becomes feasible. So when it's feasible, delta G has to be equal to or less than 0. So that means that delta H minus T delta S equals 0. So then, delta H equals T delta S. So then delta H divided by delta S would equal T. If we do that, we would get delta H, which is 676.4 divided by 0.7031. If we do that, we get 962 Kelvin. Done. Now it says another equilibrium is involved in the extraction of iron from this, as shown below. Enthalpy changes of formation are given in this table. Calculate the enthalpy of formation of CO. So the amount of people are just like, okay, right, what I'm going to do is I'm going to draw the arrows upwards and blah, blah, blah. If you've seen any of my other videos, I absolutely lose it every time when somebody does that. What you need to do is you have to construct a cycle by looking at everything in the question. Rule number 1 is write out what the overall equation is going to be in a Hess's law cycle. There's no other way around this. I don't care who you are. I don't care what you tried to do. I don't care what mystical formula you tried finding, and it somehow works. The only way to do any enthalpy change is either by a Hess's law cycle or a Born-Haber cycle. Even for bond enthalpies, I do not care who you think you are. So in this case, rule number 1 is write out the overall equation that you're going to look for that has every bit of everything in it, right? They want us to find the enthalpy of formation for CO. So the enthalpy of formation for CO is going to be the enthalpy change when 1 mole of a compound is made from its constituent elements in their standard states, right? So we're going to be looking for, eventually, every arrow in a Hess's law cycle, remember, is an enthalpy change, CO from C solid plus a half O2 gas. That's what we're trying to find. Then it says enthalpy changes of formation are given in the table below. Look at what they gave you in the table. This is the enthalpy change of formation, which is where you're making 1 mole compound from its elements. And here, this is 1 mole compound from its elements. When you're drawing a Hess's law cycle, you need to make the overall reaction link everything in together. This is a pretty good one because it's got all of this stuff in it that we want. So then Fe3O4 solid plus 4CO gas makes, if we're going this way around, can you put the reversible one if you want? Remember, every arrow is an enthalpy change, so it's going to be, what, minus 13.5, because that's what the question's told you. 3 Fe solid plus 4CO2 gas. Right, now what you do is you compare what you've got in the table, what you want and what you're looking for, to what's in the equation. So here in this table, it's the enthalpy of formation, which is going elements 1 mole compound. This is the 1 mole compound, this is the 1 mole compound. Here, this is a 1 mole compound on this side, this is the, wherever it is, 1 mole compound, although there's 4, right? It's on this side. So far, in every single thing in this cycle, we have no elements written. And here, we want to find 1 molar compound from its elements. So the thing we're going to put on the bottom of this cycle is probably going to be the elements. So that's how you decide how to do a cycle. You don't just look at the question, it says formation, and be like, oh, I'm drawing a formation one. Because what if they gave you combustion instead? Then what? You have to do it this way. There's no other way around it. Then what you do is you look, we've got elements to compound. This number they've given us, because every enthalpy change is every arrow is an enthalpy change, is going to be an enthalpy change for formation, which is 1 elements to 1 mole compound, so that's the arrow going up. In this case, again, for this CO2, there's an arrow going up. We want to find the one for CO, which is elements to compounds, it's going to be this. And you can't really do an enthalpy of formation for an element anyway, but we'll put it there. No harm doing it. Just, so here then, Hess's law says that if you start and finish at the same point, the enthalpy change is the same no matter how you get there. If I start here and I live here and Tesco's 1 mile away, does not matter if I went all the way to Australia and back, because I'm still 1 mile away from my house. So that means we can put the numbers in and then muck about with this and see what's up. So put the arrows numbers in. Enthalpy of formation of this from its elements, which is minus 8.5. Here, enthalpy of formation of CO. We don't know what it is, but the enthalpy of change of formation is 1 mole of a compound made from its elements, right? Elements to compound, we've got 4 moles, so it's going to be 4x. Here, you can't do an element to an element, so there's 0. And then here, 4CO2, they've given us 395, but there's 4 lots of it, so 4 lots of minus 393.5. So then, again, like I said, if you start and finish here, enthalpy change is the same as the other route. So that means minus 13.5, equals this, so going down this way and back up here. So if we're going against this arrow, it's going to be 1118.5 minus 4x, because we're going against that, plus 0, plus 4 lots of this, minus 393.5. I like to bracket off these so that I don't get confused with the negatives and positives. If I do that, let's just tidy this up. I get minus 13.5 equals minus 4x minus 455.5. Therefore, minus 4x equals 442. So then x equals 442 divided by minus 4, which is going to be minus 110.5. Done. That's how you do it. You'll never do it wrong unless you put the numbers in wrong, obviously. But this is it. There you go. Done. So aqueous solutions of hydrogen peroxide decompose in this equation. A student investigates the decomposition by measuring the volume of gas produced over time, and all of these are measured at room temperature and pressure. They use this much of this H2O2. From the results, the student determines the concentration of each time. The student plots a concentration time graph. So cool, this is concentration, this is time. Delta change in y, over the change in x is going to be, remember, your gradient. In this case, it's the change in the concentration of something over the change in time, which you look at that, that's a rate. Might be useful here. Anyway. So it says here, determine the total volume of oxygen measured at room temperature and pressure that the student should be able to prepare to collect in this investigation. Suggest apparatus that would allow this to be collected, indicating the scale of working. So what we need to do is we need to look at the maximum concentration that this has, because eventually all of this will produce this gas. So here, it's saying what? The volume of oxygen measured at this. So they're using 25 centimeters cubed of H2O2, and this is it, right? So the maximum moles of H2O2, so if I write that down here really, is going to be this times this, right? So the moles of H2O2 equals its concentration, 2.30 times its volume, which is 25 over 1,000. And if you do that, you get 0.0575 moles. Now, all of this will eventually produce this gas. You can see they're in a 2-to-1 ratio. So the moles of O2 is going to be this times a half, right? So 0.0575 divided by 2. If I do that, we get 0.02875 moles. The question's telling us that we need to figure out how much the volume is that they're going to end up making at room temperature and pressure. So if you've got room temperature and pressure, then the moles of any gas in the world is going to be its volume over 24 decimeters cubed, right? So in this case, it's going to be volume equals moles times 24, which is 0.0287, 5 times 24, which gives you 0.69 decimeters cubed. But if I times that by 1,000, because we want it in centimeters cubed, that is 690 centimeters cubed, right? So we've worked out the volume of oxygen they need, but the question says suggest apparatus that allow this to be collected and indicate the scale of working. So what you need to use is you need to use a measuring cylinder or a gas syringe, cylinder or gas syringe, but it has to be a size that can accommodate this. So a 1,000 centimeter cubed one. There you go. Done. So just a different experimental method that would allow this rate of reaction to be followed over time. So again, when you're looking at rates, you're looking at the change in something over the change in time. So they're measuring concentration. I think what they do, they're working out the volume of gas every single time as well. So instead, what I could do is I could just say, well, if they're making gas, they're going to lose mass, aren't they? So then we can measure mass loss. There you go. Determine the initial rate of reaction, the order with respect to H2O2, and the rate constant. You must follow full working on the lines below. So then here, when we're working out the initial rate, remember that I said the gradient is equal to the rate because it's the change in y over the change in x, is the change in concentration, the change in time. The gradient, you can think about it as this as well. Gradient is another word for steepness of a line, right? If the steepness is constant, it would be a straight line. So if the steepness is constant, the gradient is constant, the rate would be constant. Here, you can see that the line is getting less and less steep. Here you can see the line's getting less and less steep, so the gradient's getting less and less steep, so the rate must be getting less and less steep, as in it's slowing down as time goes on. So in this case, when we want to first of all work out the initial rate is going to be highest, the gradient's going to be steepest, which is here. So what you do is you work out the gradient of a tangent here like this by drawing a tangent there, because if you zoom in really close, the gradients of these two lines are practically the same. So what you do is you pick 2 points, and then you would work out the gradient of the tangent you've drawn. So what you would do is you do y2 minus y1 over x2 minus x1, right? This is your y2, that's your y1. A lot of people do it the other way around where they mistakenly say that's y1 and that's y2, so that's y2, that's y1. You can't do that because sometimes you need it to be negative. This is a downwards line, so it's negative. In this case, it's fine, but like just be careful when you're doing like Arrhenius plots or delta G stuff if it's going downwards, because you always should use the rightmost point, this way most point, as your second. Now, just for the sake of time, I'm going to skip just doing this because this rule is jank. The printing's all over the place, and I actually had to rescale this picture to put it in it because it wasn't in the paper for some reason I had. So I'm going to just quickly skip over that and say, well, the initial rate is the gradient of the tangent, which is just going to be, I'm just going to go with what the mark scheme says. Let me go have a look one sec. There, so it says 1.6 times 10 to the minus 3 mole dm minus 3 s minus 1, right? So that's the first bit. Now we need to figure out how to find out what the order is with respect to H2O2. So whenever you're saying an order, what that means is when you half or quarter or multiply something by something, what's happening to the rate. So there's two ways around doing this. One, you can test the half-life, or two, you could work out another gradient, another rate. So let's say we've worked out our initial rate, right? Then let's say that's at what concentration? 2.1, 2, 3, right? So our original concentration was 2.3. So if we half the concentration, let's see what happens. So if I half this, we're going to end up going to, what's that, 1.15. So what you do is you look for where 1.15 is, which is here, read across, and then work out the gradient of the tangent at this point now instead. So if you work out the gradient of this tangent, then you'll get the second rate here and see how it changes with the half, right? So if I then just go ahead and do that, let's just for the sake of time, I'm skipping out that. So the initial rate, this is the first, so I'm going to do the second method first, the other tangent. So the initial rate, sorry, is 1.6 times 10 to the minus 3, and that's at 2.3 mole dm minus 3, right? But then if you half it to 1.15 mole dm minus 3, after you calculate it, if I just look at the mark scheme, just for the sake of time, whoa, do you look at that? The rate is now 0.8 times 10 to the minus 3. When you half H2O2, the rate goes down by a half. So therefore, it's first order with respect to H2O2. You can't just look at it and say, oh, the shape is this, therefore it must be that. The alternative thing you could do is you could look at the half-life. So basically, you just look for how long it's been to reach that half point, wherever that was, right? Look at the time, and then do it again. So half that again, look for where it is, and if the times are the same between the two of them, the half-life is constant, then it's also first order. So you can look for that as well. So constant half-lives. Now that means the rate equation, in this sense, must be rate equals K times the concentration of H2O2. That's it. The way I like to think of it is if you double this, you're doubling that, so then you're doubling the rate, right? But if I double this, and if it was squared, then what's happening to the rate is 2 squared. And that's how I make sense of it. So here it's first order, but the question then wants us to work out what K is. So K would just equal rate over H2O2. So it would be your initial rate that we worked out from the gradient that I definitely did, 1.6 times 10 to the minus 3, over the concentration of H2O2 at that point, which is 2.3, which is going to be 7 times 10 to the minus 4. But we need its units, right? Its units is going to be, well, this rate is in mole dm minus 3, s minus 1, divided by concentration in mole dm minus 3. That goes. So the units is s minus 1. There you go. That's how you do it like that. Or another alternative you could do, if you did the half-life thing, is you could do K equals ln2 over t a half if you've used the half-life method, and that you could use 7.3 times 10 to the minus 4. There you go. This question is about equilibrium reactions. Hydrogen gas is manufactured as shown in this equilibrium. Explain in terms of Le Chatelier's principle the conditions of the pressure and temperature for a maximum yield, and then explain why the operational conditions may be different. So do it step by step. Let's talk about yield maxing, if you will. So to maximize yield, what we want to do is we want to force it to go this way, right? So whatever Le Chatelier's principle says that whatever change you make to an equilibrium, it will shift to counteract the change. So we want to shift it to the right. Okay? So number one is that I can see that the Ford reaction is endothermic. So if I want it to be going to the right, I want the equilibrium to take energy in, heat energy. If I increase the temperature, then the equilibrium will shift to decrease that temperature. Meaning, if I heat it up, it's going to absorb that because the Ford reaction is endothermic. So we would use a high temperature. And then you'd say, why? Because the forward reaction is endothermic, right? And this would shift the equilibrium to the right. And then for the pressure, well, we have 2 moles here, and then we've got 1, 2, 3, 4 moles here. So you would increase the pressure because there are more moles of gas on the right-hand side. Be careful to just double-check that gas is there on the right-hand side, right? So that's the first bit done. So you would say these two, this and that, equilibrium is just to counteract the change by, decreasing the temperature or decreasing the pressure, and then that would shift it to the right. However, the question says, explain why the operational conditions for this may be different. So here we need to talk about the differences, right, and why this isn't possible in practice. In theory, it'd be amazing to just have the highest possible, temperature ever. But we can't because high temperatures require lots of energy. You can't just jump and say expensive. All of this is expensive. You need to say why it requires a lot of energy. Right? But the other problem is that low pressures, well, if you think about it, here's 2 particles. I want them to react. It's going to take a while for them to whiz into each other and collide. Whereas if I do this, they're right there. They're going to smack into each other. Every reaction in the universe requires 2 things, or 3, or however many. It requires a collision in the right orientation, and it requires an activation energy that's high enough. You could have the perfect activation energy in the world, but if they're here and here, it's going to take ages for them to collide. So very low pressure would give you a very low rate, which isn't great, because even if we have the most... There's no point in having a really high yield if it takes years to get, anything out of it, because it's so slow. So a chemist investigates this equilibrium reaction, and the chemist mixes these two together. They compress it to this volume, and then they mix it to this, and they allow it to reach equilibrium without changing the volume, and it's got this. The temperature used, the numerical value was this. Work out the expression for Kc and the units. So Kc is going to be the concentration of your, because it's Kc, concentration of the products, and there's 2 of them here, so it's going to be squared all over reactant. So SO2 squared O2, right? In terms of its units, so it's going to be mole dm minus 3. Wait, hold on. Am I being weird? At the temperature used, the numerical value for Kc is this. Have they not just already given it there? All right, whatever. Anyway, so we're dealing with mole dm minus 3 squared all over mole dm minus 3 squared times that. So it's going to be mole dm minus 3. So squared times 1 is going to be cubed. So then what you end up with is you're going to have mole dm minus 3 to the minus 1. So its units is going to be moles minus 1 dm 3, which I find baffling because it's right there. But oh well. Then it says, determine the amount in moles of SO3 in this equilibrium mixture at this temperature, and then give your answer to an appropriate number of significant figures. The questions told you that this equilibrium mixture has this many moles of that and this many moles of this. So I can work out the concentration of SO2 by doing its moles over the volume, so 0.0540, over the volume of this container that they're in, which is 400. So 400 divided by 1,000. I could do the same for the O2. So it's going to be 0.0270 divided by 400 divided by 1,000. If I do that for each of these, I get 0.135 mole dm minus 3, and then 0.0675 mole dm minus 3. right? Now we need to find the moles of SO3. We can rearrange this because they've told us what Kc was here at this temperature too. So Kc times SO2 squared O2 will give you SO3 squared, right? So then if I want to go one step further, I can say that the SO3 is going to be the square root of this whole thing. Whoops, like that. So SO3, the concentration of it is going to be the square root of Kc, which they told you at this temperature is this. So 3.045 times 10 to the 4 times SO2 squared, 0.135 squared, times O2, which is 0.0675. And remember, that's all square rooted, which gives you 6.1204 moles dm minus 3. They want the moles of it, though, so that N equals CV, remember? So it's going to be 6.1204 times the volume, 400 over 1,000, which gives you 2.45 moles. There you go, done. This question is about the properties of reactions of ethanoic acid. Ethanoic acid is weak acid, acid dissociation constant 1.75 times 10 to the minus 5 at 25 degrees C. Assume you use the pH meter to work out the pH of this solution, and the pH is measured at this. Calculate the concentration of ethanoic acid. So write down the things you know and what you need. So pH is 2.44, right? So we can then go ahead and say, well, H plus concentration is going to be 10 to the minus 2.44. Now, they want us to find, what else do we know? We know we know Ka as well, which is whatever. And they want us to find the concentration of ethanoic acid. They want us to find HA. So we need to think, what links these three together, sorry. Now, it's tempting to be like, oh, KAH plus A minus over HA, right? But A minus is salt. Because weak acids, the equilibrium is so far to the left, these are practically the same. Here, there is no salt. So if there is no salt, that means that Ka roughly equals H plus squared over HA. Instead, that's the one you're going to use. So then, therefore, to find out the HA, all you do is you do HA is going to equal H plus squared over Ka. If we do that, we end up getting the 10 to the minus 2.44 all squared divided by the Ka, which is 1.75 times 10 to the minus 6, which if you do that, it gives you 0.753 moles decimeter cubed. There you go. Ethanoic acid is added to another weak acid, fluoroethanoic acid. An equilibrium is set up with these two. Complete the equilibrium and label the conjugate acid-base pairs. Anything in the universe that loses an H plus is an acid. Anything in the universe that gains an H plus is a base. That's it. So if I have HCl, for example, H plus, Cl minus, this is an acid because it can lose an H plus. This is a base going to accept an H plus to become this again. So that's how this whole thing works. So in this case, what we need to look at is we need to look at what's losing an H plus in this sense. Now here, one of these has to be losing H plus, the other one has to be gaining it. They've told you here that Ka for this is 2.19 times 10 to the minus 3, whereas here this is 1.75 times 10 to the minus 5. Remember that Ka essentially links back to H plus eventually, like products of reactants, right? So if this one's Ka is higher, we have more H plus, and if this one's lower, whoops, then that's going to have less. So that means that this one must have given out more H pluses. So this one has to have formed FCH2COO minus. Must have lost the H plus, right? If that's the case, there always has to be something to accept the H plus as well. So what must have happened here is that we have CH3COOH 2 plus. It will have accepted that. You can't just shove it out with nothing there. So in that case, with the labels, this has gained an H plus to become this. So that's your base, or really base 2, I should say. And this is your acid, because it can lose the H plus to go back down there again. So that's acid 2. This has lost an H plus to form this. So it's acid 1, and then here, this can gain a proton to come back to this. So that's base 1. There you go. The student plans to prepare a buffer solution with this pH. The buffer solution contains this and this. The student plans to add this much sodium ethanoate to 250 centimeters cubed of this COH. The student assumes that the volume does not change. Show by calculation whether this experimental method would produce the required pH, and show while you're working. So whenever you're doing these buffer questions, right, I do not do any other garbage that like people say. I know that eventually buffer's going to hinge on us using Ka equals H plus, A minus, because A minus is salt, and that's the only one that has A minus in it over HA, right? But these are all of the buffer, which is an equilibrium. So what I do is I always just write quick basic equations. Acid plus a base makes a salt plus water. And acid is an HA in our little, equation there for the Ka. Base is OH minus, salt is A minus, water we don't care about, it doesn't appear in any of these except Kw, and we're not using that anyway, right? Because it's an equilibrium, it's going to do a bit of mishmashing around to eventually get to where we need to be. It says show by calculation whether this would get the right pH. So we need to get the pH out of this by looking at what they did. So they're adding this much to this much ethanoic acid. Things are going to react and move about and shift and stuff. So just do it step by step. Initial moles is just when everything's mixed, end moles, and concentration. So initially, we have this much ethanoic acid, right, which is our HA. So the initial moles of ethanoic acid is going to be 0.8 times 250 over 1,000. If we do that, we get 0.200 moles. Are we adding any bases? There is no base being added here. There's no OH, so that's 0. Next, in this mixture, do we have salt? Yes, we do. We have 9.8 grams. We need to work out its moles. So it's going to be 9.08 divided by the MR of this CH3C, OONA, which is divided by 82. If you do that, you end up getting 0.111, right? And then water we don't care about. Now, these two are not going to react. There's nothing for this to react with. So at the end, we're still going to have 0.200, and then here we're going to have 0.111. If the question said they added a base, then you'd have to react these two, because then this would, react with this would go down, this would go down, and then you would make this, right? But in this case, I forced myself to do this because it makes me make sense of what's happening, right? Then we need to find out the end concentrations. So the end concentration of acid now is still going to be 0.2 divided by 250, and then the end concentration of the salt is going to be 0.111 divided by 250. Now, I know it seems a bit pointless to do that, but the reason I just do it is because it makes sure that, divided by 1,000. I know it seems a bit pointless to do that, but if I do this and make sure I understand every single step of this and what they've done, because a lot of people make mistakes, so they're like trying to react these two together, for example, assuming that that is actually the salt and so forth. So this just forces you to not screw up. In that case, our concentration of the acid is now going to be, the same as it originally was, to be honest. Again, I know it seems a bit pointless, but I promise, it helps doing this. And then here, this is going to be the concentration of the A-, the salt, which is now going to be this divided by this. If you do that, you end up getting 0.444 mole decimeter cubed. So then we want to find out H+, right? So Ka times Ha over A- gives you H+. So H+ is going to be Ka, which is somewhere in this question. Where is it? For the ethanoic acid, 1.75 times 10 to the minus 5. So 1.75 times 10 to the minus 5 times the HA we just got, or the, there, so that's 0.8, all divided by the A-, which we just worked out was 0.444, which gives you roughly, 3.16 times 10 to the minus 5. If you do pH of this, you get negative log to base 10 of this, and you end up with 4.50. Woohoo, it works, I think. What do they want to do again? They wanted to make a one of... Oh, there you go, it does. There you go. When the student prepares the buffer solution, the volume of the solution increases slightly. Suggest when the pH should change, be the same, greater, or less, or the whatever. So H+ concentration equals Ka HA over A-, right? This concentration I can rewrite as H+ over a volume equals Ka times HA over a volume over A- over a volume. Now I can make this a little bit nicer and say 1 over volume times H+ equals Ka times 1 over volume, HA, over the moles these are, by the way, 1 over volume, A-. Can you see how these two times together would have given you 1 over volume, HA, Ka, but these cancel out, that cancels out, that cancels out. Can you see how this H+ is dependent on the proportion of these two, like this divided by this? So therefore, the reason H+ is exactly constant is that the pH, well, first of all, pH is constant. Why? Because the HA, A- fraction or ratio or proportion is the same. There you go. So this question is about redox electrode potentials of feasibility. A standard cell is set up in this laboratory using redox systems 1 and 3, and the cell potential is measured. Draw a label diagram to show how this could be set up. So what we need is we need a nice beaker here. We need a nice beaker here. We need a solution. We need an electrode of some sort. We need a circuit. We need a voltmeter here. We need another electrode and this one here. Whoops, this is so badly drawn. Here. We also need a salt bridge connecting the two of these, and you're going to label it as well. So that's your salt bridge. That's your voltmeter. Then what we need to do is figure out what's in each half cell. So they told you it's 1 and 3. So with 1 and 3, we're going from Zn solid to Zn aqueous. So that means that this can be Zn solid, Zn aqueous, right? And then 1 and 3. So 3 was what? Fe3 plus, Fe2 plus? Because we're switching between two things in the same phase, you have to use a platinum electrode. You can't just do Fe2 plus and Fe3 plus because they're aqueous. There you go. And the salt bridge is there because it keeps the charge moving. Because if you move electrons through here to there, some other charge has to move around here to balance things out. So the ions within these, like the K and the NO3 minuses or whatever it's made of, do that. The electrons do not move through the salt bridge. It's just something that can carry charge. So then the standard conditions is that you need to use 1 mole Dm minus 3 solutions, and you need 298 Kelvin. Then it says predict the standard potential of the cell. So E cell equals E reduced minus D ox. So we need to figure out which one's being reduced and oxidized. So if it's 1 and 3, this one's the more negative one, so that's ox, that's reduced. So then it's going to be reduced minus ox, which is what, 0.77, minus 0.76. If you do that, you end up getting plus 1.53 volts. Done. Now it says, what's the strongest reducing agent and oxidizing agent? So if something's reducing agent, it's reducing something else, it's becoming oxidized. Whereas if it's something that's an oxidizing agent, it's oxidizing something else, so it itself becomes reduced. The more negative you are, the more you're being oxidized. The more positive you are, the more you're being reduced. So the strongest reducing agent is the thing that's best at getting oxidized here, which is the Zn, but it's the Zn solid, not Zn2 plus. You have to say what it is. You can't just say the whole equation. You need to say the specific thing. This is being oxidized this way. If you said Zn2 plus, that's being reduced, as you can see. So you have to say Zn solid. And in the same sense, the best thing that's an oxidizing agent is it itself getting reduced, which is the most positive, right? You can't just pick anything from here. It's this MnO4 minus, because this MnO4 minus is getting reduced itself, sorry, to become this. This is getting oxidized again the other way. So it's MnO4 minus. Done. Now it says electric potentials can be used to predict the feasibility. Construct an overall equation for the reactions between systems 2 and 4. Fine. You have a look at 2 and 4. We've got this one and this one. This one is more negative, so it's oxidized. This one's reduced. So what all you do is you look at the electrons. You can see there's 2 and there's 5 here. So what we need to do is we need to times this one by 5 and then times this one by 2. Oxidized means it's going to go that way. Reduced means it's going to be this way. You just combine the two of them and cancel out anything that's in the middle and you're done and dusted. Just for the sake of time, I'm just going to quickly write all of this out. So it's just going to be 2 MnO4 minus plus 6H plus 5 SO3 2 minus goes to 2 Mn2 plus 3H2O plus 5 SO4 2 minus. That's all it is. You can just do that yourself. There you go. Enjoy. This question is about the reactions of ions and compounds of transition metals. It shows the flowchart. This complex ion CuH2O62+, and it says what's the formula of these species of these responsible reactions. Fine. So here we're going from a pale blue solution to a yellow solution. This should scream to you immediately what it is. There's only one thing in this chemistry course that does that, and it's Cl being the ligand instead. Cl minus specifically, sorry. Because Cl minus is big, you can only fit 4 around this, so you're going to end up with CuCl4 minus, like that. But 2 minus, sorry, because there's 4 of them and it's plus 2, like this. Now, this is a key example that you need to know about, and I think when you think about it, the factors that affect the color of a transition metal complex are ligands, the metal ion itself, the oxidation state, and the coordination number, right? Now, obviously, you go from pale blue to, like, you know, all these other bits and bobs, like, you know, dark blue and stuff, like deep blue. I like to think of it as almost like, because this is such a more drastic change, you get a more drastic color. That's how I remember this color change. Whether it's true or not, I don't know. It's just, you got 6 versus 4, right? So ligand numbers changed, and the ligands changed as well. So it's just like a pretty fatty change, is how I remember this. Adding NH3 gives you a pale blue precipitate. Precipitates in transition metal complexes tend to have no overall charge. So what we end up with is we've got CuH2O something, and it's got no overall charge. The only thing that these can become is an OH. So it's an OH, right? Whoops. So OH, there's going to be 2 of them to give you a no overall charge. So there must have been 4 left here, like this. That's what that blue precipitate is. Or alternatively, you could say CuOH2, but there you go. Then it says if we add in excess, it becomes a solution again. So the charge is now returned. But something must have happened for it to do that. What's gone on is that you've got CuH2O 2 and NH3 4. And that's another specific example you need to know. If it's gone to a solution, you know it's going to have a 2 plus charge. Sorry, whoops as well. There you go. Then here, we've got some reaction. For some reason, when you react it with Ki, you make a white solid in a brown solution. So the brown solution, Ki, the only thing that's going to go brown here is I2. Now, if that's the case, think about what's happened to this here. It's become -1 to 0. That has been oxidized. When you oxidize something, you have to reduce something else. Something in this has to have been reduced. So what must have been reduced is that Cu. So that Cu is +2. If this has gone from -1 to 0, this has gone from +2 to +1. So you end up with Cu plus, and then some I minus thing, right? So it's going to be Cui. There you go. And the reason it's a white solid is because if you look at Cu, right, it's normally 4s1 3d10, but if it's losing 1 electron, the 4s electrons go first. It's going to be 4s0 3d10. Can you see how those d subshells are still full? If they're still full, that means it's going to be a white solid. It's going to be colorless because no, you know, it can't absorb different wavelengths of light and give you a color that's reflected. So there you go. Then it says, what's the type of reactions in reaction 1 and 2? So if we look at reaction 1 and 2, reaction 1 is a ligand substitution. Just got to lig sub because I'm short, I'm lazy. And here, I've just pointed out, it's redox. So we have a hydrated nickel-2 complex, and it's heated in a crucible to remove the water of crystallization. The anhydrous complex B is formed, the results are shown below. So master crucible and anhydrated, master crucible and anhydrous, and then master crucible. The anhydrous complex B is analyzed and found to have a molecular mass of this, and its percentage composition is this. Then this is the anhydrous complex B contains a cation C containing these things only, and cation C is 6 coordinate, contains 3 molecules of this bidentate ligand D, and exists as optical isomers. Determine the formula A, B, C, and D, and then work out and then determine the optical isomers of C. So there's a lot going on here, right? But just work with the obvious and basic stuff first. Collect what you know. So in this case, here, if we're going from hydrated to anhydrous, we can work out, using the mass of the crucible, how much water was lost. The H2O lost must have been these two subtracted, which would be 0.864. I don't really have to take the mass of crucible off because mass of crucible is here and here, so those two must have been that. That's helpful. We know that the MR of B is 309.7, and we know it's got this composition by mass, right? So one thing we can do is we can try and find out what the empirical formula of complex B is by using this. So you do Ni to C to N to H to Cl. Now, remember, B is anhydrous, so don't have to worry about the water in there. All you do is you divide each percentage by these ARs. So 18.95 divided by 58.7. C is going to 23.25 divided by 12. 27.12 divided by 14. And then it's going to be 7.75 divided by 1. And then it's going to be 22.93 divided by 35.5. If we do that, we then get 0.314 to 1.938 to 1.937 to, and then 7.75, and then 0.6459, right? And then divide by the smallest number, so divide all of these by this one here. So it's going to be a 1 to a 6.17 to 6.17 roughly to 24.6 to 2.057. Fine. So therefore, B probably has this formula, this empirical formula of NiC6N6H24Cl2, right? So then you can work out the MR of this and compare it to the one they've told you it definitely has. So the MR of this whole thing is going to be, which is 309.7, which equals the molar mass given in the question, so MR in question. Therefore, the B's formula has to be C6N6H24Cl2. So we know what B is. Done. Cool. If we're thinking about what's happening between A and B, literally write out a little equation if you want to. So A gets, loses its water to become B and H2O, right? So we could work out the mass of A by just subtracting these two, the crucible and this, right? So the mass of A is going to be what? 59.554 minus 51.257, which is going to be 8.297. So the mass of A, we definitely know, is 8.297 grams. B, we know the mass is going to be 58.690 minus 51.257, which is 7.433 grams. And we just worked out the mass of the H2O lost from over here as well, because these two differences will give you that. So it's 0.864 grams, right? Cool. We just worked out what B is. We know its empirical formula. So we can work out the moles of B, which is going to be 7.433 divided by its MR of 309.7, which if you do that gives you 0.024 moles, right? And then we can work out the moles of H2O by just doing 0.864 divided by 18. If we do that, we get 0.048. Therefore, if you put a ratio of 0.024 to 0.048, that's good. If you divide them both by the smallest number, you get 1 to 2, meaning that for every one of B, there's 2 waters. So that must mean there was the number of waters in A was 2. So therefore, A's formula has to be NiC6N6H24Cl2.2H2O. Smashing. We've sorted out this A. Now the question's told you, it's told you that B has a cation C, right? It's a cation and it only has NiCN and an H only in it. So NiCNH only. Fine. And what else do we know? It's 6 coordinate. It's got 3 molecules of a bidentate ligand D, and it exists as optical isomers. So in that case, C, let's just quickly think about what C could be. So it's got an Ni in the middle, right? Let's think about what we know. So we know that Ni is obviously the central ion, metal ion, right? Now, in this case, it's told you it's got a cation, and this cation's only got NiCN and H in it. So that must mean that this thing, the Cl2 must be like the Cl minuses in it. So in this case, we have a ligand that's bidentate, right? That's made of, how many Cs do we have? We have 6 Cs. So we're going to have 3 bidentate ligands, remember, because each one makes 2 and there's 6 coordinate bonds. So we've got 3 bidentate ligands that all add up to give you 6 carbons, 24 hydrogens, and then 6 Ns. So to me, we've got this mysterious bidentate ligand. Every single ligand in the universe has to have a lone pair of electrons. If it's only made of C, H's, and N's, it's going to have some amines in it. So it's going to have an H2N with a lone pair here, and another one because it's bidentate on the other side, right? So then, if we've got 3 of them, each one of them, and we've got the 6 N's, 6 C's, each one of them's got to have 2 N's, so it's probably got to have 2 C's in it too, like that. And then we just fill out the rest. 1, 2, 3, 4, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, right? So it's 8 hydrogens per this, times that by 3, that is 24. 2 carbons per this, times that by 3, that is 6. And then 2 nitrogens, times that by 3, you do get 6. So each of these ligands must be this here. So then, in that case, the cation C has to be Ni, and then, oh boy, H2N, CH2, CH2, NH3, 2, sorry, 3, whoops, 2 plus, like that. That's the entirety of C. And then D, the ligand itself, has got to be H2N, CH2, CH2, NH3. So now we figured out what C is, we know what D is, and now it says to draw the 3D structures of the optical isomers of C. All you do is you start by drawing the metal ion in the middle, and draw, your wedges and your bits and your bobs out, right, like this. And then you can add them in, and then add the lone pairs. So all the lone pairs, remember, on these ends in here. So NH2 like this, NH2, 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 NH2. And then you just draw the carbons. I'm going to draw it skeletally, just like that, for the sake of time. There. And its optical isomer is just going to be the mirror image of this. So Ni, wedge, da 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 da. Then it's going to be what? NH2, H2N, here. Then NH2, NH2, here. And then NH2, here, NH2, bish, bash, bosh. Done. There you go. That's that entire question done. If you do it logically and step by step like that, you will never fumble these questions in the world. Don't get thrown off by the fact there's loads of numbers here. Collect the pieces together and be like, how am I going to solve this problem? Anyway, thank you very much. I hope that helped. Please like, share, and subscribe. You know the drill. And yeah, see you next time.